quick. Okay. So today is basically the first week of November. So we have November, and then I'm not counting Saturday, the 1st, but basically the 2nd through the 8th is the first week. The 9th through the 15th is the next week. 16th through the 22nd is the next week. Then 23rd through 29th is Thanksgiving week, right? Now, I believe we have Wednesday off. Is that right, or do we just have Thursday and Friday off? So it is Wednesday.
Thursday, Friday, but
The calendar says Thursday, Friday.
library's closed on Tuesday night.
Let me just check.
Is it?
University closed on Wednesday. So, oh, there's the calendar right there. So, you'd think they'd have it on the calendar. Like, it should be like, oh, there it is. Academic calendar. So Thanksgiving, well, this is, okay, I know what to do. Let's just go to friends.edu and then students, self-service banner, and then important dates. All right, wait. They don't even have it there. They just have spring and summer 2025. Well, then in that case, I'll just go to my email and hopefully there won't be anything critical and showing up in it. And then I think I have academic calendar. There's more emails about statistics. There we go. Okay, so officially fall 2025, we have Thanksgiving break 26th through the 29th. When does that start? Yep, that is Wednesday. The 26th is Wednesday. So according to that, it says 26th through 29th. So we do have only Monday. Only Monday is our only day of class during Thanksgiving week. Okay, so then after that, we have basically 1 week to get ready. So 1st through the 6th, and then we have finals week, 8th through the 12th finals. So I already know pretty much what's going to be on the final. So I don't want us to necessarily have to be studying for the final just during this week. I think it'd be cool if we could actually start taking the final during this week. Maybe I could break the final into 2 or 3 parts. So that's what I usually do in my algebra classes is I give like part of the final on Monday of this week, part of the final on Wednesday, and then part of the final on Friday. And if we don't get it done on those 3 days, if I'm running behind schedule, then I'll do part of it on Wednesday and part of it on Friday, and then the last part actually on the final day during finals week. So my goal hopefully would be to do it. Oh wait, you can't see what I'm writing. Sorry, my fault. My goal hopefully would be to do it during that week, December 1st through 6th. On that Monday, Wednesday, and Friday, or a combination of those, and then you wouldn't have to necessarily come in one more time during finals week. Would you be supportive of that, or would you rather are you traveling during that week before finals and you only can come back during finals? Is anybody going to be gone before the 12th of December? Okay, so you could potentially do it during finals week, so we don't necessarily need to try to get a day ahead. What about Thanksgiving week? Is anybody going to be gone on the 23rd? Are y'all going to be here for that Monday class? Okay, perfect. What? You'll probably be gone. Okay. So that really basically means that we pretty much only have basically 2 more full weeks of class, basically, of regular classes. So that means we probably should start turning our attention slightly to what's going to be on the final and kind of going through everything and wrapping everything up. So that's kind of what my goal was to start with today. There's just a little tiny bit of more material, maybe involving trees and things like that for us to talk about. But I'm going to kind of go through that in the structure of a kind of our final exam review instead of doing it just like a whole thing coming out of the book. So with that in mind, let's go ahead and just kind of go through this thing one problem at a time. I might skip some things though if we haven't learned about them yet, and then come back to them. All right, so, and probably should have actually uploaded this file for you. Okay, so I was working on a practice final exam. Unfortunately, the last teacher who did this class didn't have any like software or online homework system, which those systems make it easy to show problems that have like tree diagrams and things like that on them. So without having that kind of software available, everything that I assigned just has to be like from the book, which doesn't have that many like different pictures and things in it. But let's just try our best. Okay, so let me do new whiteboard and let me go back to the computer. I'm gonna just see if I can search the internet and find some software program that can show us this. Prim's algorithm app. Let me see if there's like maybe an online app that can like show that to us. Okay, here's a cool one, maybe a video of it. Let's see, I'm just gonna click on this. Okay, so this is called a spanning tree of a connected undirected weighted graph G. Okay, let me share this on my Zoom window so other people can see it. Okay. A spanning tree. It's loading on Zoom. Right, let me wait. A spanning tree of a connected undirected weighted graph G is a subgraph of G that is a tree and connects, in other words, spans all vertices of G. A graph can have many spanning trees, but a minimum spanning tree of the graph is a spanning tree of the graph that has the smallest total weight among the various spanning trees. So basically, is the quickest way to get from every possible point to every other possible point. Okay, so let me click on the next one. Next one. Visualization. Okay, originally they're all colored with the standard black color. So by the way, just to give you some notation, these points are called vertexes. These points like the number 8 and 3, those ones are called vertexes. Or vertices is the way that they actually say plural of vertex is called vertices. And these are called edges. These lines between the vertexes are called edges. So, and the number beside the edge is called the weight of it. So basically it takes 10, it's a distance, you can think of it as a distance. So a distance of 10 between those two, distance of 10 between those two, distance of 8 between those two, like that. So there's 3 different sources: edit graph, input graph, example graph. Kruskall's algorithm. Basic idea. Prim's algorithm, that's what I want to do. Okay. So it's picking new elements to join to the orange result. So it's showing what it's doing. I'll explain what it's doing in a second though, once it's finished. It's going too fast to explain it in real time. Okay, so I think it's done. So basically, it's found a minimum spanning tree, a minimum weight spanning tree of the original graph. So these edges have been removed. And now every edge in the graph has been connected, but with the shortest possible weights being used. So for example, it takes a longer trip to go from, let me choose the mouse. It takes a longer trip to, like if you wanted to go from 2 to 8, it would take 13 miles to get to it that way. Now, by the way, this is not to scale. So like obviously a diagonal would usually be shorter, but in this case, that's actually a longer trip. Maybe it goes over some mountains or something like that. So it doesn't use that trip. So the way Prim's algorithm works is it begins with an arbitrary vertex. In fact, you can pick any vertex you want. The reason it doesn't matter which vertex you choose is because at the end, all the vertexes will be in, or vertices will be included. So we could start with this one, or we could start with any of them. Doesn't matter. And then you'll look at all the other edges and vertexes in the graph. And well, actually, so whatever one you started with, you look at all edges that connect to it. and you pick the one with the smallest weight that joins that vertex to a vertex that's not been included yet in the tree. So let me see if I can go back to the beginning of the problem. Okay. So they began with 0.0. Now we could have begun with 0.1. In fact, I wish that they would randomize the beginning point to show you how you can start with any point that you want to. But if you start with 0, what is the only possible edge that's connected to 0? What's the weight of it? The one that says 10, right? So you have only one choice. You join that edge with orange connected to the 0.1. Now, look at all possible edges that connect an edge and a vertex that's in the orange colors. Look at all possible edges that connect to one of the points that are in orange now. And pick the one with the smallest weight. Which one would you get? So do you see how the 8 is the smallest weighted edge that connects one of the included orange points to a point that's not yet included. So we're going to go with the edge that says 8. And then 6 is going to be included in the tree next. Now look through all the possible edges that are connected, that connect. So what you do is you look at all possible edges that connect one of the points. So all these points over there that are not in the tree yet to one of the points that is in the tree. So there's 3 orange points in the tree right now. And you want to find an edge that you want to find all possible edges that connect a point that's not in the tree yet to a point that is in the tree. And then out of all those edges that you find, you want to choose the one that has the smallest weight. So we could do this edge, this edge, this edge, and that edge. 1, 2, no, okay, 1, 2, 3, 4. 4 edges we could choose that connect a point that's not in the tree yet to a point that is in the tree. So let's fast forward, see which one gets picked. So I think they're turning black when the code is considering them. So it's considering them all, and it picked the top one. Now there's another one it could have picked. Does anybody see the other one that it could have picked? So it could have picked this one over here instead of that one up there because they both have a weight of 10. You see that? So you have a choice sometimes. If you have 2 choices, it's basically up to you which choice to pick, and then neither one of them is wrong. So there's not necessarily a specific choice on only one and only choice sometimes. So remember when we had these 3 points, this point, this point, and this point, we could have picked the 2. There's actually 3 that have a weight of 10, right? There's this one, and there's that one that all had a weight of 10. We could have picked either of them because they all have the same weight. So your answers do not necessarily have to be exactly in the same order. Okay, perfect. There we go. So then it's done. So there's not necessarily one right answer, but you are guaranteed to get the tree that has the minimum weight. So there's probably more than one tree that also has a minimum weight. It's not necessarily a unique answer. But there we go. That tree connects all the vertices together, all the vertices together with the smallest, with the pathways that have a total weight that's the smallest. Okay, there we go. Let's try to see if we can do that with a practice problem. So let's see. Wow, it's just really hard with no actual homework system to even use. Okay. Well, do you have a way of bringing your book up with you? It should be about page 845 or so, if I remember right. Let me look in the index. It's been PRIM, Prim's algorithm, 835, okay. 835. Okay. Let me see if there's any homework problems for this. Okay, perfect. Yeah. Homework question number 2 through 4. Okay, cool. So can everybody look on page 839 of your books at problem number 2? Let me see if I can bring this up on the internet as well. So this is called Discrete Mathematics 8th edition by Rosen. Discrete Math 8th edition, Rosen. Okay. And then go to page 839, right? Hold on, let me minimize, let me move this like over to the side. I don't think the page numbers of the book actually match the page numbers of the PDF though. Yeah, so page 839 is actually page 816. So that's 23 numbers behind. So we need to go to what's 839 plus 23? That'd be 859, 862. Okay, so here it is. Let's look at one of these questions. Let's look at question 2. So did everybody see question 2? Okay, perfect. Now I'm going to take a picture with my phone. Hold on, how do I move this over to the, there we go. Okay, I'm going to take a picture of that with my phone, if I even have my phone. There it is, okay. And then let's try to solve it. Okay, perfect. So I'm going to stop sharing the window now. And I'm going to start sharing whiteboard. Okay, perfect. All right. And it's actually kind of simple to understand. And this algorithm was actually invented before they even had computers. I think it was 1930 or so. So question 2, point A. Well, my phone went to sleep. Exact worst time. So there's point A, point B, point C, and point D. And then point E, in fact, in the middle. And then there is a connection between A and C that has a length of 4. Then there is a connection between A and B that has a length of 1. Connection between C and D that has a length of 1. Connection between B and D that has a length of 3. And then the connection between C and E that has a length of 3. Connection between E and D that has a length of 2. Connection between E and B that has a length of 3. Connection between A and E that has a length of 2. So 1, 4, 2, 3, 3, 2, 1, 3. So I'll let you pick. Pick a random letter between A through E. Pick a random letter between A through E. C. Okay, good choice. So let's pick C. And it could have been any of them. So we're going to add C. Anything that I circle is now included in the graph. So this, the original graph is everything, but we're creating a new minimum spanning tree that connects all the vertices A, B, C, D, and E with the minimum total weights that can be done. So look at all the edges. That means the connections between the vertices. So look at all the, okay, let me color the vertices in a different color so you can see which ones are the vertices. C, D, B, A, and E. Those are the vertices. So now look for an edge that connects a vertex that's been included in the minimum spanning tree with a vertex that's not been included yet. So there's 3 options. Which of those 3 options has the smallest weight? So what are the 3 options? What are the weights of the 3 connections that connect from point C to a point that's not included yet in red? Yep. And which of them is the smallest? Yep. So we're gonna pick point D along edge 1. So let me color that edge right there in red, and I'll circle the point D as well. Now, Now look at all possible edges that connect a point, or a vertex, I shouldn't say a point, a vertex that's colored in red already with a vertex that's not colored in red yet. So there's edge number 4, right? There's edge 3, there's edge 2. Now, by the way, those edges are not that they don't really have an identity, they just have a weight. So there's 2 edges that are both have the same length of 3. So there's this edge, there's this edge, there's this edge, and there's this edge. Which of those has the smallest weight? D to E, right? So we're gonna include that one in this. We're gonna add that connection and that vertex to the minimum spanning tree. And then we'll keep going until there's no vertices left that have not been colored red yet. So look at all the edges now that connect a point that connect a vertex that's not colored red yet with a vertex that is colored red. Look at all the edges that do that and pick the smallest weight. D, E to A. Yep. E to A. So we're gonna pick that edge right there. That's E to A because that's the smallest one. Circle A. It's now included in the minimum spanning tree. And now pick the smallest edge that's remaining that connects to a point, a vertex that's not colored red yet. Yeah. So it's pretty simple in this example. So now I'm going to draw the new minimum spanning tree. It's B, A, E. No, this tree is a subtree of the original one. And then C. And that's 1, 2, 2, 1. Yeah, so there's no tree that connects those 5 vertices together with a total weight that's less than that. So now this doesn't say that it's the fastest possible tree connecting every single letter together. For example, in order to go from B to D in this tree right here, you'd have to go from here to here, then to here, then to here. If I would have had the direct connection from B to D in the original graph, it would have only taken 3 steps to go from B to D. So this is not saying that every fastest path is included to go from any point to any other point directly. But it just says that this is the tree that has the smallest total path that it still includes all the vertices. So is that kind of easy to understand? Do you have any questions? Okay, so that's Prim's algorithm. So have you ever heard the word prim and proper? So now that you know Prim's algorithm, you can feel prim and proper. Prim's algorithm. Okay, so we learned that. The next thing we need to learn, so that's the first thing I see that's kind of like a new topic on the final review. Okay, the next question that's, wow, I just wish that we had a system about this. Let me actually try to I'm gonna try to see if I can maybe email myself this file that I'm looking at. Got to work like 20 minutes early and I was gonna do this, but then I talked to somebody the whole time about that issue that I mentioned before. So that's my fault. Okay, personal. It just says loading. Nothing works right when you need it. That's fine though. Let's go on to something that we can do without a picture of it. So let's just kind of review. So question number 1 on, let's just do question number 1 on the final review actually. So question number 1, I'm just gonna start the final review. So question number 1 on the final review says, let C equal D. They're both equal to the same set. -3, -2, -1, 1, 2, and 3. So it's -3, 2, 1, -1, and then so basically 3, 2, 1, and also positive, negative and positive 3 and 2 and 1. That's what the numbers are. And then it says, we just talked about relations, remember? So this is about a relation. So for every X and Y value that are an element of well, okay, this is, I think there's a formatting mistake in this, but I think it's supposed to say C cross D. That means that when it says X and Y are in C cross D, that means this means X is an element of C and Y is an element of D. So basically it means X and Y are both -3, -2, -1, or 1, 2, and 3. So for every element of those sets, X and Y is in the relation S, means that 1 divided by X minus 1 divided by Y is an integer. So it's not a fraction, it's an integer. So can somebody say, give me this question, is 2 S2? Is 2 related to 2? So S is a relation. S is a relation, anything that contains ordered pairs technically is a relation. So is 2 related to 2? So what does it mean if 2 is related to 2? That means is the point 2, 2 an element of S? So S is defined, so definition of S is that a point is in S if 1 over X minus 1 over Y is an integer. So is 2, 2 in S? And how do we know if it's in S? Okay, finally stop saying loading. Is 2, 2 in S? Is 2, 2 in S? What do you think? And there's, by the way, there is one other thing I want to cover besides just a final review. But we're going to start with this. Is 2, 2 in S? Is it or not? Yes, and why would it be in S? Because 1 over X minus 1 over Y, which is 2, is equal to 0, which is an integer, right? Can anybody think of any other numbers that are in S? So the answer is yes. So 2 is S2. By the way, in the notation 2 S2 is the same as saying 2. I talked about relations called R. The name of a relation can be any name, though, that you want. The 2 S2 means the same as 2 R2. This means 2 is related to 2, which means the point 2, 2 is in the set S. So is 2 S2? And the answer is yes. Can anybody think of any other points that are in the relation? So the points are 1 point X is related to a point Y if 1 over X minus 1 over Y is an integer. Can anybody think of any other points that might be in the relation?
So long as X and Y equal each other, it should be.
Yeah, so long as X and Y are equal to each other. So what? Not necessarily, but it is one way. So basically you're saying that X is always related to itself. What's the name of that property? X is always related to X because 1 over X minus 1 over X is always equal to 0, right? And notice there's no zeros in it, so you don't have to worry about dividing by 0, because the point, there's no value of 0 in the sets C and D. C and D don't have the number 0, so you can't divide by, there's no X value of 0 that's possible. So you can't have a 1 divided by 0. So for any points in this set, 1 over the number minus 1 over the number is always 0. What's the name of the property of relations if X is always related to itself? What's the name of that property? The relation is called what if X is always related to itself? Not recursive, reflexive. Yep. Can anybody think of a number that's not equal to itself that's related?
One and negative one.
Yep. 1 is related to -1 because 1/1 minus 1/-1 is actually equal to 2, which is an integer. Can anybody think of any other numbers that are related? What about, is 2 related to -2? Yeah, because 2, 1/2 minus 1/-2 is equal to 1/2. Is everybody watching? 1/2 plus 1/2, right? Which is 1. So that is an integer. Yep. So that works. That works well. So you kind of get the idea, right? So let's write the set S. So now that you understand what S means, let's try to write all the points that are in S. Do you think you can do that? So what is the actual literal contents of the relation? Remember, a relation is defined as a set of ordered pairs that define every x value that's related to the y value that it's related to. So S would equal, we know for sure that they would equal -3, -3, because those are related to each other, -2, -2, -1, -1, +1, +1, +2, +2, +3, +3, right? And then what other points did it contain? So you said 1 is related to -1. What about, is -1 related to +1? Yep. And we know that 2 is related to -2 because you'll get +1 from that. What about, do you think -2 is related to +2? Yes, because you'll get -1 if you add those together. So I think that's pretty much it. So those are the only points that are related within that set. Okay, let's go to question number 2. Okay, that involves a diagram. Let's look at question number 3. Okay, that does not involve a diagram. We can do that one. So question 3. Write the statement in symbolic form. So let P equal the phrase X is greater than 6. Q is the phrase X equals 6. And R is the phrase 10 greater than X. So let's try to write each of these inequalities as combinations of those letters P, Q, and R. So if I had the math equation inequality X is greater than or equal to 6, how can I write that using the symbols P, Q, and R? What does X is greater than or equal to 6 mean? It means P or Q, right? X is greater than 6 or X equals 6, which means P or Q. Let's try to write 10 is greater than X is greater than 6. Let's try to write that math inequality using the symbols P, Q, and R. So what does that imply? 10 is greater than 6 is greater than X. What does that imply? It implies what? It implies, say that again? P, yep. It implies X is bigger than 6 for sure. And it also implies that 10 is bigger than X also, right? That implies P and R. And then let's try this one. 10 is greater than X is greater than or equal to 6. What would that one, how would I write that inequality using symbols P, Q, and R? So what do we know for sure? So. Well, we don't know.
Maybe P and R or Q and R.
Yes, I think so. So, but there's one thing we know for sure, just one of those facts we know for sure just on its own though. R. Yep, we know for sure that 10 is greater than X. So we know R, so I'm gonna start with R and then say and. So whatever, no matter what else happens, we always know R is true. So it's an and, R has to be true and something else has to be true. The other two things that have to be true are an or. So they don't, neither one of them has to be true on their own. It's just one or the other. So R always has to be true. And then either X is equal to 6 or X is greater than 6. So either P is true or Q is true, like that. So R is definitely true and either P or Q is true. So the P or Q goes in parentheses and the R is just by itself with an and after it. Okay, that's perfect. Okay. Now let's look at number 4. Okay, the train. So make sure you're taking notes because this is getting you ready for the final. The train is late or my watch is fast. The train is late or my watch is fast. The train is late or my watch is fast. How do I write that? How do I write the negation of that? The negation of that is what? Now it says to use De Morgan's laws to write the negation. But whatever way you do it, you don't have to necessarily use those laws, but whatever way you do it, you have to write the negation of it though. So what's the negation of A or B? What's the negation of the statement A or B? Well, but yeah, but that's just the answer is, that's like saying the answer is the answer. So what is it? So if you have the statement not A or B, so the statement itself is like saying A or B. So that obviously the negation of A or B is not A or B. But what is not A or not or B equal to though? Right. The negation of A or B is not A and not B. So the negation would be the train is not late and my watch is not fast. So there we go. Okay, let's look at question number 5. Okay, that's a truth table. Let me skip that one. Okay, okay, this is a good one. Let's go back to number 7. It says, suppose P and Q are statements, and it's known that P implies Q is false. That's the only thing you know. You don't know what P and Q are. You only know that P and Q implies Q is false. Find the truth values of these. What is the truth value of not P implies Q? What is the truth value of P or Q? What is the truth value of Q implies P? So that's it. So this is a difficult puzzle for you to logically figure out. So if it's known that P implies Q is false, then what can you conclude about those other 3 expressions? Let me let you think about that for a brain twister for a little bit. And then, by the way, let me grab the attendance page and do attendance real quick. So today is the 11/5, and there is Amani. Let's see. Wait, no. Here. Amani. Chris, not here. Okay, then. LaShawn, good job. And I don't see Anthony. I do see Zoe. Isaac, that's you, right? Okay, perfect. No, I don't see Noah. Anthony Johnson, that's you, right? Okay, perfect. Colin, that's you, right? Perfect. Ignacio, is that you with the cap on? No, that's Isaac, right? Okay, yeah. Sorry, I already forgot that was Isaac. Okay. So Ignacio is not here. Caleb, that's you, right? Okay, perfect. Arturo, that's you, right? Good job. Taylor, that's you. Logan, are you here, Logan? Guess not. And Mercada. Okay, perfect. Good job. So which of those did anybody figure out whether any of those is true or not? Did anybody figure out if any of them is false? So this is actually kind of a trick question because remember that we learned that the only time a P implies Q represents a promise, and when's the only time you've actually truly broken your promise? Is what? If somebody else did their part of the bargain and then you didn't follow through with your part, right? So P implies Q. If we know that that's false, I actually tricked you and said we don't know what P and Q is. We don't know what they are, but we can logically figure out what they are though. Because if P and Q's implies Q is false, that means that when you made a deal with somebody and they first person followed through on their part of the deal, so they did it, and the second person broke their part of the deal, right? So if we know that P implies Q is false, that can only happen when the first part of the promise was kept, then the second person broke their end of the deal, right? So anytime you see the P implies Q is false, that means P is true and Q is false. So that means we can actually think about it like this. Replace P with true and replace Q with false. Because we know that P actually is true and we know that Q actually is false. So replace P with true, replace Q with false, and replace Q with false, and replace P with true. Now is it easier to answer the question? Now, which of those three statements is going to come out to be true or false? So let's look at the middle one first. That's the easiest. In order to be true, an or statement only needs to be partly true, right? So is it true that true or false is true? Yes, that is true. That one is a true statement. And then let's look at the last statement. If the scenario is like a promise, if you make a deal with somebody and they do not do their part of the deal, but then you feel nice anyway and you still do something for them, like if somebody says, I'll pay you $100 and then you can take pictures of me or whatever. And if they didn't pay me $100, but I still did something for them, I've just been extra nice. I haven't broken my promise, right? So this is still true. False implies true is still true. So that's fine. What about not true implies false? What is the opposite of true? So not true implies false is actually just saying false implies false. And is that true? Yep, that's true. So false implies false is like saying we made a deal and they said that if you mow my yard, I'll mow your yard. And then the first person didn't mow my yard, so then I didn't mow their yard. So nobody broke their promise. They just decided not to do the whole deal. So that's still no promise has been broken if that happened. So that they're all true. So any questions about that? Okay, perfect. Okay, that's very good. We have 3 minutes left. We have 3 minutes left. Let me just tell you one more thing for you to start looking up on your own. So there's something called finite state machines. Finite state machines, and we're not going to get into them a lot. Finite state machines. But we're going to talk about one specific thing that's extremely important for computer science. Has anybody ever heard this word before called regular expressions? Have you ever heard that word? Raise your hand if you've ever heard of the word regular expressions. Any of you heard of that word? Okay. maybe a little. So we're gonna talk a little bit about regular expressions as well. And so we're gonna talk about regular expressions, Markov chains. And then other than that, we're basically just gonna be reviewing for the final. Those are pretty much everything else in the class. So, but you can go ahead and jump ahead. If you want to look up on Google some things about regular expressions or Markov chains, you can go ahead and do that. So that's all for today. Keep up the good work. And by the way, I think maybe some people in here who